Okay, so we are going to hit the last week of the semester. So let me just do a few things quickly that we have, what we have not done, and then we will come back to these questions uh, towards the end of the class. Okay, so one of the things that I think we have not done is, so this is not going to be kind of a what is called a continuous stream. There will be some topics, so we will discuss topic by topic. So first thing is we talk about spin. Okay, so as I told you earlier that we have, so a particle like electron, so you know that electron has orbital angular momentum given by L. Then because of this orbital angular momentum, so due to this, due to L, it has, it exhibits, it exhibits a magnetic moment, which whose magnetic dipole moment is given by E by 2m into the angular momentum L. But it is observed that electron also has an intrinsic magnetic moment. Electron has intrinsic magnetic moment. Okay, so let me call this as mu L, or maybe I can call this as mu S. As I told you, historically it was thought that spinning motion is there, and it turns out from the observation that this will be equal to, if you can say that there is an angular momentum associated with that. Okay, as I told you, it's a mathematical construction. So you can say that there is a magnetic moment like this. So now so you have something called Stern-Gerlach experiment. Where you have a beam of spin-half particles. Let's say you have a beam of spin-half particles, and then you have some Stern-Gerlach apparatus. So this is kind of a poles of electromagnet. The shape is different to produce an inhomogeneous magnetic field. And then you will see that if you have a screen somewhere here or detectors somewhere here, now this beam will split. Okay, so something will go up and something will go down. Okay, so this is what you get, spin half particles. That is, there is a quantization in terms of two beams, so that spin will have two values. Okay, so this will be in some particular direction. Let's say this is z direction, so we are going to measure sz component, and sz component has two eigenvalues. That is, it has an angular momentum of h cross by 2 or minus h cross by 2. Okay, so this is, of course, you keep this uh, Stern-Gerlach apparatus along x, then also you will have two values. You choose any direction, there will be two values if this beam is arbitrary. Okay, so this is the kind of experiment which was done by Stern and Gerlach to say that there is a two-valuedness. Okay, so it is, since if you consider only spin, okay, so if you consider only spin, then you forget about other degrees of freedom. There are only two states, right? So one you can call it as up spin, and the other you can call it as down spin. Okay, so for example, you can say that I will denote this as up z. Okay, so up z. So when sz, up z is an eigenstate of sz with an eigenvalue h cross by 2 up z. And similarly, you can have down z, which is also an eigenstate of sz, which is having an eigenvalue minus h cross by 2 into down z. So since there are only two values, these are orthogonal to each other. That means if it is up z, it does not come to the downward beam. So these are orthogonal. So if we are studying only spin, okay, the spin degree of freedom alone, that is if we confine to study the spin, then we have we have two-dimensional complex Hilbert space, which is somewhat same as the Hilbert space of polarization states of classical electromagnetic wave. Okay, so the Hilbert space corresponding to this one is simply T2, that is two complex numbers, which is equal to, you can say that this is kind of x comma y, such that x comma y is in complex numbers. So this kind of a Hilbert space describes this one. Now once you know that every state has this kind of a thing, then Sz is a Hermitian operator, and Hermitian operators eigenstates will form a basis. So we can call that as Sz basis, just to say that it is eigenbasis of Sz. Okay, so which is up z comma down z. These two basis vectors. Okay, so we can identify kind of a matrix notation for this. So what does this matrix notation tell you? We can say this up z is equal to 1 0 and down z is equal to 0 1. So we can write like this. Now if we choose this basis, then you can define something called sigma vector, which is equal to h cross by 2 into s vector. That means sigma x, sigma x, h cross by 2 will be taken out, and then we define the sigma vector. So that sigma x, sigma y, sigma z are matrices because they are operators, and h cross by 2 is factored out. So the eigenvalues of sigma x and sigma y are just plus minus 1. Okay. So for example, sigma z operator, when you operate it on this up z, you will get simply up z. The eigenvalue is plus 1. Sigma z operator, when you act it on down z, you will get minus down z. So the eigenvalue is minus 1 and so on. So if you want it to be like this, now you can, this has to be eigenvector. So from these two equations, or the requirement of these two equations, we can see that the sigma z can be written as a matrix like this: 1 0 0 minus 1. Okay, So these matrices you can also write sigma x to be equal to 0, 1, 1, 0, and sigma y to be equal to 0 minus I 0. Okay, and these matrices are called Pauli matrices, as you might already know. And there is an interesting thing is that if you consider for a vector space of complex 2 by 2 matrices, what is the dimension of this vector space? Which is 4 dimensional, because there should you require 4 complex numbers. It is 4 dimensional. The set given by identity matrix sigma x, sigma y, sigma z. These 4 matrices form a basis. That means any complex 2 by 2 matrices can be written as a linear combination of Pauli matrices. Okay, so this is very useful, even though we may not use it now, but later if you go to study something called density matrices, etc., this will be very useful concept. Okay, so now what is uh, important to understand here is that you ask a question. So suppose you take sigma x. Sigma x is equal to 0, 1, 1, 0. Now you ask what are eigenvalues of sigma x. Okay, even without solving, we should be able to find out, because I told you in whichever direction you put, it will divide into h cross by 2 minus h cross by 2. So it has to be plus minus 1. So eigenvalue of sigma x are plus minus 1. Okay. Now we can ask a question. What are the eigenvectors? Okay, what are the eigenvectors? So let us ask eigenvectors of sigma x, which I may denote in the abstract notation as up x, comma down x, such that when sigma x is acting on up x, I will get up x. If sigma x acting on down x, I will get minus down x. So in matrix form, suppose I want to find out for the eigenvalue plus 1, what is the eigenvector? Okay, so I must write 0, 1, 1, 0 into an eigenvector which I do not know. I will call it as alpha beta is equal to plus 1 into alpha beta. That is the eigenvalue equation, right? Plus 1 into alpha beta. So this gives me that alpha is equal to beta. Okay, both the equations will give me only alpha is equal to beta. So the eigenvector, okay, so this up x is proportional to alpha alpha. Since alpha equal to beta, I will write it like this. So I can normalize this one. Okay, so normalized eigenvector has to be always normalized, because that should be the unit vector in that direction. So normalized so normalize it, then you get 1 by alpha root 2 into alpha alpha. So that is equal to 1 by root 2 into 1 1. Okay, so I have shown you that up x is represented by a matrix which is equal to 1 by root 2 1 1. And notice that I can write this as 1 by root 2 into 1 0 plus 0 1. But what is 1 0 and 0 1? as I already written earlier, that is up z plus down z. Up z plus down z. So up x can be written as up z plus down z. Similarly, I will leave this as an exercise. Okay, show that the eigenvector for -1. Okay, so the eigenvector for -1 is given by down x, which is equal to 1 by root 2 into 1 minus 1. Okay, so that implies your down x can be written as 1 by root 2 into up z minus down z. Okay, 1 by root 2 into up z minus down z. Okay, so you can do this exercise. So repeat this exercise with the operator sigma y, which is equal to 0 minus I 0. Okay, needless to say that eigenvalues are plus minus 1, and up y can be written as 1 by root 2. I will leave it for you to show this 1I, and down y can be written as 1 by root 2 into 1 minus I. Okay, so that yeah, so that you can say that this up x, up y can be written as 1 over root 2 into up z plus I times down z, and down y is equal to 1 by root 2 times up z minus I times down z. Now I want you to take a look at this. Okay, maybe let me write down here so that you don't have to scroll up. We had already written earlier that up x is equal to up z plus down z divided by root 2, and down x is equal to up z minus down z divided by root 2. Correct? So now you can see that suppose if you are suppose if you are suppose the state is up x. Okay, now I ask measure sigma z, which is sz essentially. Measure sigma z. Then ask what is the probability to get a result plus 1. Suppose if I ask this question, what will be your answer? Measure sigma z. What is the probability to get result plus 1?
1 by 2.
Huh?
1 by 2.
Yeah. So the answer is 1 by 2.
So 1 by 2.
Yeah, very good. So answer is 1 by 2. Okay. And suppose if I ask measure sigma y. Sorry. Okay. Now let us say state is up y. Okay. and repeat this. I'm the same question. Measure sigma z, and what is probability that your sigma z is equal to plus 1? Okay, what is the probability in this case?
Half.
Huh?
Half.
Here also it is half. So now if you see that probability of getting plus 1 or minus 1 is half half, whether the state is up x or up y. Okay, so we cannot distinguish these two states. Okay, so suppose if I give you probability. Okay, so now if I say, uh, so I am saying that construct a state, construct a state such that such that when sigma z is measured, probability of getting plus 1 is equal to half, and probability of getting minus 1 is equal to half. Suppose if I ask you this question, which state will you construct? Construct says such that when sigma z is measured, probability of getting plus 1 is half, and probability of getting minus 1 is equal to half. So what state would you construct?
Can use both sigma x as well as sigma y.
So you can say sigma, it can be sigma x or it can be sigma y, correct? Because when probabilities are given, okay, when probabilities are given, you know that um, so up z plus down z both should be there, and there 1 by root 2 and 1 by root 2 should be there. Okay, but there are infinitely many states, because I could have always multiplied this one with some phase, right? Suppose if I take e to the power I phi, okay, some phi less than 2 pi greater than or equal to 0. For any phi, if I construct a state like this will satisfy the requirement, correct? You follow this, no? So I can say that this is, I don't know, maybe let me call this as state phi itself, because I'm having this phi as a symbol here. So let me call this as phi, or some alpha of phi. So let us call this state. So how many states can I construct? I can construct infinitely many states, because for every value of phi, this probability of plus 1 is for this state, no? The probability of plus 1 is half and probability of minus 1 is half. Do you understand this? So this phi, this phi is what is called a relative phase. Relative phase. So if you give probabilities alone, then relative phases we will not know. And also notice that if, for example, if our vector space is not defined on the complex numbers, but it is defined only on the real numbers, then you are going to this particular problem. So this particular problem has only two solutions. What are the two solutions? Up x and down x. That's all. Because plus or minus, only two possibilities are there. Whereas if you say that it is a complex number, then there are infinitely many possibilities, because I could have put phi to be anything here. That will give you a new state, correct? And in quantum mechanics, we observe, for example, in this case itself, we have seen up x state has to be represented, up y state has to be represented, and probably you have to represent any other state. X and Y are two directions, but I could have taken some other direction. Okay, so that also can be represented in terms of upset and downset, right? So, so you can say in general, we can parameterize. Suppose, let's say that uh, in general, so let n cap be an arbitrary uh, unit vector. Unit vector characterized by by angles theta and phi. Okay, angles theta and phi. What does that mean? That means your n cap can be written as sine theta cos phi into I cap plus sine theta sine phi into j cap plus cos theta into k cap. Okay, so these are called direction cosines, right? So sine theta cos phi, sine theta sine phi, cos theta, direction cosines. Modulus of n is 1, so that is why it is called a unit vector. So let it be an arbitrary vector. And we are interested in sigma n, which is equal to the sigma vector dot n cap. Okay, and let's say this is the operator that we are interested in. Okay, and then we have states that are eigenstates of this operator, which we will call it as up n and down n. Just like I have up x and down x, we can talk about up n and down n. Okay, now you want to ask what are the, so sigma dot n cap is what? So you have sine theta cos phi into sigma x plus sine theta sine phi into sigma y plus cos theta into sigma z. Correct? So this is your sigma n. Your sigma n is going to be this. So you can write this as a matrix, right? So what will be this matrix? Cos theta sine theta into cos phi minus I sin phi sine theta into cos phi plus I sin phi and minus cos theta. So this is what this equation is, right? So I could have written this in this fashion: cos theta sine theta into e to the minus I phi sine theta into e to the I phi minus cos theta. So this is the equation, right? Now, I mean, without doing, you can say eigenvalues of this equation are plus minus 1. Why? Because you notice that sigma n square is equal to identity. So eigenvalues of sigma n square are all 1. So that means eigenvalues of sigma n has to be plus minus 1. So eigenvalues of this matrix has to be plus minus 1. So suppose if I ask what is the eigenvector corresponding to plus 1. So eigenvector for plus 1. Okay, so that is, let's say I have cos theta sin theta e to the minus I phi sin theta e to the I phi minus cos theta into xy is equal to plus 1 into xy. So that is my eigenvalue equation. So you have x cos theta plus y sin theta. This x and y are not coordinates. Please don't get confused with that. So if you want, you can put some other symbols, maybe alpha, beta. So let's say alpha and beta sin theta e to the minus I phi. Okay, so that's equal to alpha. And sin theta e to the I phi alpha minus beta cos theta is equal to beta. Okay, so now I can simply write this as um, I I can solve this, right? So I can say beta is equal to alpha sin theta e to the power I phi divided by 1 plus cos theta. Okay, so I substitute it in that equation above. So that is equal to alpha times 1 minus cos theta is equal to alpha sin theta e to the power I phi um, okay, so yeah, so alpha is beta is equal to this. So then what we write is uh, your alpha beta, okay, should be written as uh, alpha into alpha sin theta e to the power I phi by 1 plus cos theta. So now we have to normalize this one. So how do we normalize? So mod alpha square plus uh, mod alpha square sin square theta divided by 1 plus cos theta the whole square. Okay, so this is your square root of this is your norm. Okay, so that's equal to alpha times so let us write this as 1 plus cos theta the whole square plus sin square theta divided by 1 plus cos theta the whole square to the power half. So this becomes 1 plus cos theta, okay, and that's equal to 1 plus 2 cos theta plus cos square theta plus sin square theta, that becomes 1. So there is 1 divided by 1 plus cos theta the whole square to the power half. So we have alpha into 2 into 1 plus cos theta, correct? 2 into 1 plus cos theta divided by 1 plus cos theta, the square to the power half. So that is equal to alpha into root 2, okay, divided by, or let us put this way, alpha times 2 divided by 1 plus cos theta. But 1 plus cos theta can be written as 1 plus cos theta can be written as 2 cos square theta by 2, correct? So that is equal to alpha, there is a half here, so alpha by cos theta by 2. So this is the norm of this vector. So that means now my alpha beta this vector can be now written as cos theta by 2 divided by alpha into alpha sin theta e to the phi sin theta into e to the I phi divided by 1 1 plus cos theta. Okay, so now the first equation, the first one will become cos theta by 2. Second one will become uh, cos theta by 2 into the sin theta. I can write it as 2 sin theta by 2 cos theta by 2. Cos theta by 2 into e to the I phi divided by 1 plus cos theta. I will write it as 2 cos square theta by 2. Correct? So 2, 2 will cancel. This cos square theta by 2 will cancel with this cos square theta by 2. So what we have is cos theta by 2 into sin theta by 2 into e to the power I phi. Okay, so this is the eigenvector corresponding to what? Corresponding to this up n. Okay, that is plus minus 1. Okay, so your up n is given by this cos theta by 2 and sin theta by 2 into e to the power I phi, which can be written as cos theta by 2 into up z plus sin theta by 2 into e to the power I phi down z. So you can write an arbitrary vector like this. So if you take up x, then what happens? Your theta is equal to 90 and phi is equal to 0. That will be your x-axis. So you can get any values. So if you have this kind of a state, now suppose if state is phi n, and then measure sigma z, and then you want what is the probability to get plus 1, that is cos square theta by 2, and probability of getting minus 1, whatever is the value of I, it is sin square theta by 2. So that means there are infinitely many vectors that you can construct with this kind of a probabilities given. Okay, so I will leave it as an exercise for you. Exercise, find expression for downside, down n. Okay, now you can find it the way I have found earlier, but you can also do an inspection. That means you want it to be orthogonal to this, correct? You want it to be orthogonal to this. When can that be orthogonal? So by inspection, requiring this down n up n has to be equal to 0, they have to be orthogonal vectors. We can write down n to be equal to, okay, so down n has to be equal to sin theta by 2 into up z minus cos theta by 2 into e to the power I phi down z. So when you take this one first, if you take inner product, you get sin theta by 2 cos theta by 2 and minus cos theta by 2 sin theta by 2, and e power I phi, e power minus I phi will go away. So you have this. So this I am just doing this by inspection, but if you want to get some practice, you can try to find out what is the eigenvector for this operator sigma n, okay, for this operator for eigenvalue -1. So if you do that, then you will get this this result. I have just shown this by inspection. Okay, so this is one part that I wanted to show you. And how do we integrate this concept to quantum mechanics? Is that so in quantum mechanics, suppose you have a particle, okay? So for example, in hydrogen atom, so for hydrogen atom, the uh, electron wave function, electron wave function is written in the following fashion, right? Psi n l m r theta phi. Okay, r theta phi are the coordinates and nlm are the quantum numbers. And is a common eigenfunction, of uh, these three operators, right? Hamiltonian, L square operator, and LZ operator. So this is a common eigenfunction of these three operators. Now suppose if we consider, okay, so if spin is considered, if spin is considered, then you have two more operators. Okay, if spin is considered, we have to consider common eigenstates, of Hamiltonian, L square, LZ, and there is some S square and SZ. Because for every angular momentum, L square and LZ or S square and SZ, you have to. So that means your wave function will have N, L, M, N, L, M, S, and then there will be some MS. Okay, so there will be 5 quantum numbers associated with this. Of course, spin does not depend on these classical variables, I mean the coordinates r, theta, and phi, so that will have a separate. So usually this wave function can be written as, so you write down some wave function which depends on r, theta, phi. This is called the spatial part of the wave function, spatial. And then you multiply this with S and MS, a spin part of the wave function. Okay, spin part of the wave function. Okay, what we have discussed earlier is a spatial part of the wave function. Now you have to discuss the spin part of the wave function. Spin part of the wave function is what? It will be something like this one, right? So it will be up spin, down spin, and things like that. Okay, so this kind of notation is there. So normally what happens, suppose if you have a spin half particle, okay, then we can say you can define something called a spinner. Okay, what is a spinner? You talk about psi, okay, I do not know, maybe let me call it as psi 1 here and psi 2 here. This is like two component of wave function, psi 1 and psi 2. Psi 1 corresponding to wave function of spin up particle, and psi 2 corresponds to wave function of the spin 2 particle. So instead of working with one wave function, now we have to work with two wave functions. Okay, so Pauli developed a theory working with this kind of a spinors. Okay, so same Schrodinger equation, now you solve with a spinor, and where your Hamiltonian will involve this sigma, which is a 2 by 2 matrix. So your entire operator will be operators of 2 by 2 matrices. So that is what it is. So wherever there is no spin, then you have to put it as an identity of 2 by 2 matrix. For example, if you say that you have a kinetic energy does not have spin term. So it will be p square by 2m, 0, 0, p square by 2m. Like that, we have to modify the equation. So instead of one Schrodinger equation, you will get a 2 by 2 matrix of Schrodinger equation. And then you solve that one to get uh, spin incorporated into the non-relativistic quantum mechanics. But this is, as I told you earlier, yeah, is a artificial adding up of spin to the formalism of non-relativistic quantum mechanics. Spin naturally appears in relativistic quantum mechanics, as I mentioned earlier. So from Dirac equation, spin automatically comes because the Dirac wave function is a spinor by itself. It's a four-component spinor actually, not two-component spinor. And if you just take non-relativistic limit from there, then you will get this spinor equation which Pauli has derived. Okay, so this is something which I want you to understand. So I would recommend to read first chapter of modern quantum mechanics by J. Sakurai. So this chapter has got nice introduction to spin and Stern-Gerlach experiment, and he tries to explain all features of quantum mechanics using Stern-Gerlach experiment. So that is a very, I mean, when that book came, it was very new, but that book was itself 25 years or 30 years old. So I would recommend you to take a look at that chapter. Okay, so I am not going to say much about the spin further. Okay, so let me now go to the next topic. Okay. So I think I've spent 1 hour. So the next topic is what is called addition of angular momentum. This is very important. That is why I thought I should spend some time. Addition of angular moment. Okay, so we can see, let's say that you have an electron. Electron has got an orbital angular momentum. It has got spin, and hence the total angular momentum should be orbital angular momentum plus spin. Or you have two spin particles. One has spin S1, other has spin S2. Then you want to consider a composite system. Then it will be total spin of the particle will be S1 plus S2. So in general, we should have an understanding of how to deal with uh, when we try to add two angular momenta. Okay, so for that, let us try to develop a theory. So let J1 vector and J2 vector, I'm going to call them as J1 and J2. J1 vector and J2 vector be two angular momenta. It can be of a same particle or it can be of two different particles, it doesn't matter. And let capital J is a vector sum of this J1 plus J2. Okay. Now, considering, so consider only J1. Consider J1. Okay, then we have, so if we consider only one angular momentum, we work with common eigenstates, common eigenstates of operators j1 square and j1z, correct? Just like L square and Lz, we work with j1 square and j1z. Okay, so let us denote.
So here J1 and J2 represent angular momentum of two different particles, right?
That's what I said. There can be two different particles, or there can be two different angular momentum of same particle. Like one can be orbital angular momentum, other can be spin.
Right.
Yeah. So I am trying to be very general. That's why I called it as J1 and J2. So let us denote those states to be J1 comma M1. J1 and M1 are quantum numbers associated with them. Okay, how many such states are there? Okay, so your M1 can vary from minus J1 to plus J1. That means these states will become a basis for a 2J1 plus 1. Okay, so let H1 be the Hilbert space. Okay, so state space. And this space is 2J1 plus 1 dimensional space. Okay, and this is the basis, correct? So this is the basis, that is J1 comma M1, M1 going from minus J1 to plus J1 is the complete orthonormal basis. Basis of the Hilbert space H1. Now the same description, so whatever I have written here, okay, so we can repeat for J2. That means there will be a Hilbert space H2, which will be 2J2 plus 1 dimensional. Now consider the composite system. Okay, so now consider the composite state space. So which I will call it as H, which is H1 product H2. Okay, H1 product H2. So that means dimension of H is equal to 2J1 plus 1 multiplied by 2J2 plus 1. So this is the dimension of this composite state space or composite Hilbert space. Now what is the basis? Okay, so the basis of H, okay, there are two ways to choose the basis. Okay, first way is common eigenstates of J1 square, J2 square, J1Z, J2Z. I can take common eigenstates of these. They commute among themselves. Okay, so note that this is SESCO. This is a complete set of compatible observables. And let us denote this basis as J1, J2, M1, M2. So this is essentially a direct product basis. Okay. So this basis is J1, M1 product J2, M2. That's all. So this is a basis. And since M1 goes from M1 has 2J plus 1 and M2 has 2J plus 2J2 plus 2, that will have so many 2J1 plus 1 into 2J2 plus 2 members. So this is a basis. Okay. And there is another way to choose a basis. That is common eigenbasis, common eigenstates, states of uh, J1 square, J2 square, J square, and J Z, capital J square and capital J. Okay, so this is another CSU. This is another CSU. And let us denote this as J1, J2, capital J, and capital M. Okay. Now let us try to denote this. Since J1 and J2 are common in these two bases, so we will try to denote this in shorthand as simply M1 comma M2, and you denote this as J comma capital M. Okay, so we should keep in mind that J1 and J2 are a part of this, but just for writing purpose, let us simply write this because J1 and J2 are there in both of these bases. Okay, so we could have chosen to work with any one of these bases. Okay, now the question is that so we have to ask two questions. That is, so what are the values of quantum number J, okay, quantum number J given J1 and J2. So this is one question which we can ask. Now because this is a vector, okay, so let's say J1 is a vector like this. Let's say J1 is a vector like this, and J2 is also a vector like this. J2 is also a vector like this. Then what will be J1 plus J2? J1 plus J2 is going to be addition of J1 and J2. The magnitude of J1 plus J2 will be addition of J1 plus J2, right? If they are in the same direction. Okay. So in this particular case, capital J is equal to J1 plus J2. Okay. Suppose if J1 is like this and J2 is like this. So J1 is like this and J2 is like this. Then what happens? Your capital J is equal to J1 minus J2. But this can be positive or negative, so we take modulus of this one. And in any other direction, it is going to be between these two, correct? So we we say that your J should take values from J1 minus J2 up to J1 plus J2. Of course, this has to be an integer, and hence it has to be in units of 1 you have to add, correct? So just to tell you that, suppose just to give you an example, suppose let's say j1 is equal to half and j2 is equal to half. Okay, so example A. Then what will happen? Capital J is equal to half minus half, and you write half plus half. Okay, half plus half. Half plus half is 1. This is 0. In between there is nothing. So this is equal to 0 comma 1. So J will be 0 or J will be 1. Okay, so this is one example. Let's take another example. Let's say J1 is equal to half and J2 is equal to 1. Okay, then what happens? J1 minus J2 is equal to half minus 1, that is equal to minus half. But we should take modulus of that one, that is equal to half. That is modulus of J1 minus J2 is equal to half. And what is J1 plus J2? J1 plus J2 is equal to half plus 1, that is equal to 3 by 2. Okay, so half plus 3 by 2. Half plus 1 is 3 by 2. So your J will have half and 3 by 2. So these two values this J will take. Okay, so suppose you take as a third example, J1 is equal to 1 and J2 is equal to 3. Okay, then what happens? J1 minus J2 modulus is equal to 2. Okay, and J1 plus J2 is equal to 4. So your J can have values 2, 3 and 4. Okay, so this is how you have to find out what are the allowed values of J.
So,
Okay,
so capital J cannot be negative anytime.
yeah, capital
The
J,
values of
yeah, yeah. Okay, so now we understand how what are the values of, so this question we have answered. Okay, so now it is possible that we can we can so now the question is that if you take, so so note that we have this m1 comma m2 and j comma m are two bases. But we can ask a question. Can I represent one element of second basis in terms of the first basis? Okay, so it must be possible. Okay, so it must be possible to represent, that is, a vector Jm can be expressed as a linear combination of elements of basis. Okay, so maybe let me call this as basis B1 and let me call this as basis B2, basis B1. That is possible, right? Okay, and the coefficients of this expansion, okay, so coefficients of such expansion are called Clebsch Gordon coefficients. Clebsch Gordon coefficients. Okay. So formally we can represent them like this. Okay, so our next task will be to find Clebsch Gordon coefficients. Okay. So the thing is that your Jm, okay, Jm can be represented as, so I can say that we can have C, let me call it as Jm here, and M1 comma M2 here into M1 comma M2. Of course, this has to be summed over all this M1 comma M2. Okay, so M1 will go from minus J1 to plus J1, and M2 will go from minus J2 to plus J2. So these coefficients are called the Clebsch Gordon coefficient, or in short, CG coefficient. Okay, so we have to understand how to get this coefficient. These coefficients are very important for reasons that we will see. Now, so let us try to again get hang of this idea by looking at examples. So first, let us try to look at an example of.
Sorry, your voice is not clear. Thank you, sir.
Yeah. So first, let us try to take an example of J1 equal to half and J2 is equal to half. Half and J2 is equal to half. Okay. And then we notice that, so if J1 is equal to half, then what should be M1? M1 can be minus half and plus half. If J2 is equal to half, then M2 can be minus half and plus half. So now we have, you can write down this M1, M2 basis. M1, M2 basis. Okay, what is M1, M2 basis? And remember, this is two-dimensional. This is also two-dimensional. So the Hilbert space is four-dimensional, because 2j plus 1 is 2 here. 2 into half plus 1. So I must write 4 basis elements. So they are something like this. Half, half, half minus half, minus half, half, and minus half, minus half. Okay. So that is our M1, M2 basis. Now we have already seen that we know that this capital J can take values from modulus of half minus half to half plus half. So that implies that is equal to 0 and 1. So your capital J can be 0, in which case your capital M is also equal to 0. Your capital J is equal to 1, in which case your capital M can be minus 1, 0, plus 1. Okay. So your Jm basis basis. Okay, so you want to write down Jm basis. That is 0, 0, 1, 0, 1, 1, 1 minus 1. So this also has a 4 elements like this. Now we must write every element of this Jm basis in terms of M1, M2. The corresponding coefficients are called the Clebsch-Gordan coefficients. Now, to do that, we have to understand one thing. Okay, so to find CG coefficients, note that there is a constraint that capital M has to be equal to M1 plus M2. Because capital M is what? The projection of the total angular momentum along Z axis, and M1, M2 are projections of J1 and J2. So when you add them, these projections have to also get added up. So capital M is equal to M1 plus M2. Now this one will simplify our job to some extent. So let me tell you how do we do it. So what I will do is that I will try to give a geometrical trick. So let us say that I am going to say M1 axis is here and M2 axis is here, and then represent each one of these M1, M2 bases in terms of some points. So like for example, I have a point here, and this is basically representing a state half comma half. And then I have a point here which is representing a state half comma minus half comma half. Okay, the first one is like x coordinate, second one is like m2 coordinate, right? Then I have a point here which is representing minus half minus half. And then I have a point here which is representing half minus half. Okay, so I have put 4 points, and these 4 points are associated with these 4 M1, M2 bases. This is just a representation. Now, you know the values of capital M. Okay, if you see capital M values are minus 1, 0, plus 1. This is also M equal to 0, right? So if this M1 plus M2 has to be satisfied as capital M, that means now I will draw lines, okay, corresponding to capital M values. So capital M is equal to 1. That is basically, it is coming only from this point. So let's say this is capital M is equal to 1 line. Capital M is equal to 0 can come from these 2 points. So this is capital M is equal to 0 line. Capital M is equal to minus 1 will come only from this point. That is capital M is equal to minus 1. From this, we have a great simplification in the sense that since capital M is equal to plus 1 will come only from one state. When I expand capital M is equal to plus 1 state, I will get only one particular. Okay, so because of this constraint, we can write the following. That is 1 comma 1 state has to be equal to half comma half. No other state is there, giving rise to capital M equal to M1 plus M2. And we can also write 1 comma minus 1 is equal to minus half minus half. There is no other state which is giving rise to this. Essentially, it means the Clebsch-Gordan coefficients for half half is 1, and for all other things is 0 in this expansion. But when it comes to 1, 0, 1, 0, 1, 0 can come from both of these states, half minus half and minus half half. So I must say that is some C1 times half minus half plus some C2 times minus half half. Okay, so this is how it C1 and C2 have to be determined. Same is the case with 0 0, because m is equal to 0 can also come from these two, half minus half and minus half half. So that we do not know at this moment. So let us call that as some d1 times half minus half plus some d2 times minus half half. So now we have to only determine these 4 coefficients, right? So you see, instead of 16 coefficients, we have just 4 coefficients now. So this diagram has simplified our job considerably. We require to now get only these 4 coefficients. Okay, now how do I get these coefficients? This is also very simple. All that we have to do is the following. Okay, so remember, so recall that you can define something called J plus operator, correct? You can define something called J plus operator. When J plus operator is acting on Jm, what will you get? You will get some factor here, square root of something, and then you have J m plus 1, correct? So if we put a minus, then this will become m plus or minus 1. And then there is a factor here. Okay, so I think we have looked at that factor earlier. That is j into j plus 1, okay, minus m into m plus minus 1. If I remember correctly, m into m plus minus 1. Okay, so this is the factor that you have in the, so if it is j plus or j minus, this is the factor that we have. Okay, so this is one result that we already know. And also note that this j plus operator is same as j1 plus operator plus j2 plus operator, because j equal to j1 plus a2, j1 plus j2 plus operator. So what I am going to do to find out C1 and C2, okay, so to find C1 and C2, okay, operate j plus, I think j minus on left hand side, and j1 minus plus j2 minus on right hand side of equation 1 comma 1 is equal to half comma half. Okay, so on this equation, left hand side you put j minus, right hand side you put j1 plus and j2 plus. So let us try to do that. So j minus acting on 1 comma 1 is equal to j1 minus plus j2 minus acting on half comma half. Okay, now remember the values of j1 and j2 are half only. These are values of m1 and m2. Okay, so that means this is nothing but j1 minus acting on half half plus j2 minus acting on half half. Okay, that I have two different terms on the right hand side. Now what will the left hand side be equal to? Left hand side is equal to square root of j is equal to 1. So 1 into 1 plus 1 minus m is also equal to 1. So 1 into 1 minus 1, because this is j minus, correct? 1 into 1 minus 1. And what should be this? This is 1 0. That is my left hand side. Now what is right hand side? So remember, this is M1 and this is M2. So J1 minus will actually change M1. J2 minus will actually change M2. Correct? So that is equal to, you have square root of half into half plus 1 minus half into half minus 1 into minus half half plus, of course it is going to be same here, plus half minus half. So this is what you will get here. Correct? Now what is this half into half plus 1? This is 3/4 minus half minus 1 is half. So this is basically 1. Okay, so this factor is 1 and this factor is root 2. So what I have is this 1 0 is equal to 1 by root 2 into half minus half half plus 1 by root 2 into half minus half. So please read this one and the equation that I have written earlier. So I have determined C1 is equal to C2 is equal to 1 by root 2. Okay, so we have C1 is equal to C2 is equal to 1 by root 2. Okay, now we have to determine D1, D2. Okay, so to determine D1, D2, use that this 0, 0 has to be orthogonal to 1, 0. Okay, so if it has to be orthogonal to 1, 0, I think without doing any work, by simple inspection, you can show that this 0, 0 has to be equal to 1 by root 2 times minus half half minus 1 by root 2 times half minus half. Okay, when you take it like this, coefficients, this will become orthogonal to that. So we have solved all the Clebsch coefficients. We have represented every state in JM basis in terms of M1, M2 basis. Okay, so this is the problem of representing the problem of finding the Clebsch coefficients. Okay, so now I want you to little bit practice. So maybe I will leave this as an exercise. Okay, so now what you do is you try to take solve CG coefficients for J1 is equal to 1 and J2 is equal to half. So as we have already seen, capital J will be equal to half and 3 by 2. Okay, so this is 3-dimensional and this is 2-dimensional. So capital J will be 6-dimensional space. Okay, so it will be little more involved than this, but it's not very difficult. So please try this, follow the same steps. The important thing is this diagram. Okay, so if you learn to write this diagram, then a lot of simplification will come. Okay, so these diagrams are not probably taught in the textbooks, but we have to, learn them by just doing with our. When you are solving problems, then you do a lot of hard work. Then you realize, okay, there is a simplification, and then if you practice that, then you can solve the problem in much easier way. Okay, so this is one topic I wanted to cover, but I wanted to also make this slightly more general. So this problem is something, so let me just make this connection. So the Clebsch-Gordan problem is a very general problem. So it is like this. Suppose you have some kind of a. So let us say that we have a. So we have a Hilbert space. And then there is some symmetry group. And this symmetry group has certain irreducible representations. Okay. Now let us say that some d alpha and d beta, let's say, be two irreducible representations, irreps. Now we can ask a question: what happens to d alpha cross d beta? This will also be a representation. This is a direct product. This is also be a representation. So is also a representation of the group, but reducible. Okay, but reducible. Now you can ask a question. So we can represent this d alpha cross d beta as sum over, okay, sum over some gamma into, you can have nu alpha, beta and gamma into d gamma. Okay, that means this is reducible, so it can always be decomposed in terms of irreducible representations, right? So these coefficients are called Clebsch-Gordan coefficients. Okay, so essentially what we are doing in quantum mechanics is an exercise like this. So this has a very general, since we are learning some irreducible representations, I am making this connection. In quantum mechanics textbooks, they may not make generally, but this is called the Clebsch-Gordan problem. Clebsch-Gordan problem is taking a direct product of two irreducible representations and recasting that as a direct sum of the representations like this. Okay, so this is what we have as a Clebsch-Gordan problem. Okay, so now notice that in an angular momentum setting, okay, so in angular momentum, your so if you take your L comma M, okay, so if you are taking a Hamiltonian like L square by 2m or L square by 2I. If you are taking a Hamiltonian like this, particle on a sphere or a rigid rotor, some kind of a system like this, then the energy eigenvalues will depend only on L. That is h bar square by 2I into L into L plus 1. Correct? So they don't depend on M. So EL is independent of M. Okay. So this is because the Hamiltonian is invariant under any rotation. Okay. So Hamiltonian is what we say is has rotational invariance. That means there is a group which we call as SO3. This is a group of proper rotations in 3 dimensions. This is a continuous group, and it is characterized by some 3 Eulerian angles, which you might have studied in rigid body dynamics, or it can be characterized by 1 angle and 1 axis. So there are different representations: axis angle representation, 3 angle Eulerian angle representation, like that. So one can there are 3 parameters, and these 3 parameters are 3 angles. So you have a continuous group. Now one can talk about irreducible representations of this group. Now the irreducible representations of this group, when you represent on the uh, Hilbert space of this particular system, and since each EL is independent of M, so for a given EL, you have a 2L plus 1 dimensional degenerate subspace of the total Hilbert space H. Okay. Now this degenerate subspace will become an invariant subspace under the action of this group. Okay. So because of that, we have a 2L plus 1 dimensional irreducible representation. That implies, so 2L plus dimensional irreducible representation. And for different L's, it will be 2L plus 1. Like for example, if L is equal to 0, it's a 1-dimensional representation. L is equal to 1, it's a 3-dimensional representation, and so on and so forth. Okay, so it's an infinite dimensional vector space, so you can have infinitely many irreducible representations. But every irreducible representation is basically a 2L plus 1 dimensional irreducible. So it is this irreducible representations. Okay, so as you can go back and see, J1 means there is a 2J plus 1 irreducible representation. J2 means you have a 2J plus 1 irreducible representation. When you are taking a product, that representation is like taking a direct product of 2 irreducible representations like this, and then that can be represented back as sum of the irreducible representations, and that is where we have this Clebsch Gordon problem. So I'm just trying to make this connection so that you appreciate the link between the symmetry and group representations and the Clebsch Gordon problem. Okay, so this is one aspect, and I just want to initiate one more, and I think I will pick it up on next class. So as we have been talking about various problems, so we have something like exactly solved problems, like that. If you take list exactly solved problems, Okay, so there are problems like particle in 1D, 2D, 3D box. This is basically infinite well problems. Okay, so with some difficulty we can solve some potential well problems. Potential well or hill. Okay, so you have this tunneling kind of problems. And third is, of course, harmonic oscillator. And fourth, of course, we have solved spherically symmetric problems. Okay, so one of the problem is rigid rotor, and of course, hydrogen atom. So I don't know if you have read for Feynman lectures. B. Balakrishnan of IIT Madras, he wrote a foreword, and there he says, why in quantum mechanics only these problems are solved? And he says, a witty answer he himself gives, saying that these are 5 marks questions or 10 marks questions, whatever. Okay, so that is why these problems only are solved. But the answer actually is that there is nothing else that can be exactly solved. Okay, so what all can be solved, we solve it in the first course on quantum mechanics, and everything else will be has to be solved in an approximate way. So rest all quantum mechanics has to be solved using approximate methods. Okay, so basically so far what you have learned is kind of it's like alphabets of quantum mechanics, and the business will start only when you try to, because anything that you want to do in real life, anything that you want to do, any calculation you want to do, you should do it only using approximate methods. Okay, so there are 3 approximate methods that so first one is called perturbation. Okay, so this is basically time independent perturbation. Time independent perturbation. So this can be done in 2 ways. Suppose if you have all the energy levels are non-degenerate, okay, then there is a way to do it. And if they are degenerate, then you have to slightly be careful. So non-degenerate perturbation theory or degenerate perturbation theory. Then you have something called variational technique, and then you have something called WKB approximation. Okay, so these techniques are kind of independent. You can learn each technique independently. Okay, so I will concentrate in the next 2 lectures to discuss perturbation theory. Okay, and I request you to learn variational and WKB approximations from the lectures which I had given earlier, and they are already available. I will share those links. Okay, so please learn these 2 techniques, that is variational technique and WKB approximation. I don't think I will have time to discuss them in this course. So, but I request you that lecture is available. So you please take a look at them. Then you can. So if you have some questions or some doubts, I will. We can discuss sometime. But um, I am not planning to cover them here. But it is available, and well in advance you can take a look at them, and if there are doubts, then we can discuss. Okay, I will share those links. Perturbation theory is one thing which I will do it in some detail. So in the next two classes, so that um, that can be learned. That there is no lecture, so I will try to do that here. Okay. So with that, I think we will complete the semester. Any questions? There is another important thing called time-dependent perturbation theory, which will be a part of your Quantum 2 course, the third semester. Time-dependent perturbation theory, quantum theory of many particle systems, and scattering theory, together with relativistic quantum mechanics and some rudimentary concepts of field theory. I think this is what will be your quantum mechanics too.
Sir, I have two notes, sir, in this
Yeah.
lecture. One is that you told that we can take two ways of writing the basis, right? One is JM basis and other one is J1 squared, J2 squared, J1 Z2. Like first thing I understood, like J1 square, J2 square, and J1 is a J2 is a part of the elements of those 2J plus 1 Hilbert space. But how you got J, capital M, and J1, J2? So then how you got this capital J, capital M?
I have to look for any four mutually commuting operators, right?
Yes,
So
yes,
capital J square will commute with J1 square, J2 square, and also J1 Z.
yes.
So I can form those four operators as a complete set of compatible observables.
No, sir, I'm like trying to connect it with the elements of the Hilbert space. There, the four elements are part of the Hilbert space. 2J plus 1, 2J plus 2. Because this J, Z, and J2Z are part of those Hilbert space. But here, this J and M, capital J, capital M, how you got suddenly got into this? Because J equal to capital small J1 plus small J2 and capital M is M1 plus M2. Is it something like that?
Yeah, that is correct. But what I'm saying is that uh, the first basis you are able to understand because it is just a product basis,
Yes, yes, sir, exactly.
correct? So, but we can
Yes,
have non-trivial basis, right?
yes, yes, yes.
So this is one such non-trivial basis.
Sir, and second, while you're forming the table, there you wrote 1, 1, 1 minus 1, 1, 0. I understood those three. But how you wrote the last one, sir? 0, 0?
I mean, how did I find those D1 and D2?
No, no, no. D1 and D2, I got it. I got how to get it. How do you get 0, 0 from the diagram? Diagram, how you are able to form that 0, 0 basis from diagram?
See, for 0, 0 and 1, 0, capital M value is 0 only, correct?
Yes, sir.
So
Yes.
that M equal to 0 line will pass through those 2 points, minus half, half, and half minus half. So any state with capital M is equal to 0 will be a linear combination of only those two states. Whether it is 0, 0 or 1, 0, it doesn't matter. Capital M is what is important.
Oh, here we only worry about the M state, not the J state.
Correct.
So the J state, why it doesn't have 0, 1 and 0 minus 1, sir? Why we are not regarding those two things?
No, this
Taking
is,
the,
see, for any given J, M will take values only minus J to plus J. If J equal to 0, the only allowed value M can take is 0.
Okay, here we already prefixed that j equal to 0 and 1. Only two values we are able to, we are trying to
That is
find.
that is because given J1, J2, the J values are fixed. No, that
Okay,
is
yeah,
what
yeah,
we
yeah.
have discussed earlier.
Yes, 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 yes. Okay, sir. Okay, okay, sir.
Yeah,
Yeah.
Excuse me, sir.
yeah, yeah,
Sir,
yeah.
I didn't got the point how multiplicity is related to dimension of Hilbert space.
Multiplicity.
How multiplicity is related to dimension of Hilbert space.
Yeah. So suppose if you take, suppose what you have is only a system of a particle of angular momentum j, correct? You are only worried about angular momentum. Earlier, I made a statement that if you are considering only spin degree of freedom, okay, spin half particle, then the Hilbert space is two-dimensional. Why did I say that?
Yes,
Because once I consider only spin, then rest of the space is not important for me. I will only look at what is the Hilbert space corresponding to spin degree of freedom. In the same way, if I consider only angular momentum as a system, or the system's angular momentum as my concern, then the Hilbert space of interest will be only 2j plus 1 dimensional Hilbert space, right? Because m will take only values from minus j to plus j.
yes, sir.
So
Okay,
essentially, what I am trying to say is that I am only considering angular momentum degree of freedom. That's all. All other degrees of freedom I am not interested at this moment. And the state space corresponding to that degree of freedom will be 2j plus 1 dimensional.
sir. It is for LS coupling also. If we consider twice S plus one into twice L plus one, then it will also be dimension of Hilbert space.
Yeah, yeah, correct.
Okay, yes, sir. Got it. Sir, another doubt. What is the importance of spinor in this spin?
No, spinar is actually a representation of, I mean, basically, when you are trying to solve Schrodinger equation, you will get a wave function, right?
Yes,
Now, suppose if the system has a spin degree of freedom, then there is a two valuedness, correct? It can be
yes,
upspin or it can be downspin, like that. So that two valuedness, if you want to represent, then you write two wave functions: one wave function for spin up, one wave function for spin down.
yes, sir.
So like that, you have to represent two. For example, let us say uh, you have psi, and I want to say that this particular particle, suppose let's say electron in the ground state of hydrogen atom, is in up state or down state. I want to represent, so I will write psi 100 and 0 as a column vector. If it is in down state, 0 and psi 100 as the column vector. Okay,
Yes, sir.
so that I know that this is representing spin half up spin particle, and this is representing down spin particle. Now I can construct something like an arbitrary spin state, right? Then I will have to write down a column vector with two components.
Yes, sir. So this ket vector is spinor.
Ah, so basically, you are now. I'm just writing this as a wave function. Okay. So if you
Yes,
want
sir.
to talk about a ket vector, then you have to say that okay, there is a ket, and then two different kinds of kets. One a component, two components of ket.
Yes,
There is no difference with respect to spinor notation whether you use ket or a wave function.
yes, sir. Understood. Thank you, sir.
Yeah.
Sir, and this SO3,
Yeah. Yeah. Go ahead.
Excuse me, sir.
Yeah.
Sir, I couldn't understand like while writing the JM basis, like we have all possible combination except -1.
Except what? -1.
-1 and -1.
See, when you do angular momentum problem, you say that your angular momentum quantum number j will go from 0 to infinity. It cannot be negative, correct?
Yes, sir.
So j
So
cannot
that's
be,
why we have.
j cannot be negative. So j can start from 0. That is why we take modulus of j1 minus j2.
Okay.
And then you can go up to j1, j2.
Sir, two doubts, sir.
Yeah.
So when you have taken this sigma n as a general vector, unit vector, and so you've taken this as a like a sigma n equals to sigma dot n, then we get sine theta cos phi sigma x and all that.
Yeah.
So then you have represented in a matrix form. So how did you get that matrix form? Oh, by just taking the
Sigma
matrix
is,
forms of sigma x, sigma y,
yeah,
sigma.
yeah, yeah.
Okay, okay. And so, secondly, is so for the we have calculated the upper n, and then so we have by inspection seen that it is orthogonal to down n. So down n we have calculated as sine theta cos minus cos theta e to the power something.
Yeah.
So as a linear superposition. So actually we can get some other state also which is orthogonal by taking say sine theta by 2 e to the power I phi and minus cos theta. So is
What
that yes, so
what
yes.
I wrote, no?
So if we take the so I think this e to the power I phi will be negative, right? So we have to cancel the positive e to the power I phi.
So when you take a raw vector associated, that e to the I5 will become e to the minus I5.
Okay, sir. And we can do the same for e to the so if you take e to the power I phi in the sine part.
Okay. So if you have to do that, then you have to do e to the I5. So then that is fine. So you are saying there will be an overall phase which you can ignore. That's what you're saying.
Yes, yes, sir.
Yeah, yeah, that's correct. So
So that
see, overall phase we are not bothered because any state in quantum mechanics can be described only up to a phase factor.
is there a possible downstate then?
That is not a different state. What I'm trying to say is if you put e to the power I5 sine theta by 2 up z and e to the okay, wait a minute. So then it is e to the I5 but it will not be orthogonal. That's what the problem is, isn't it?
So maybe not or
Not orthogonal. That's what it looks
yeah, the
like.
probability when taking a mod maybe it will disappear,
Ah,
but okay, so
orthogonality will be a problem.
okay, so,
I think it's a unique representation.
so uniqueness is there. That's my main
Yeah,
question.
yeah, yeah.
Sir, in the final case of the lecture, you talked about SO3 group, which is actually a representation of the Hamiltonian, right?
Huh, huh.
Sir, so this SO3 group, can you said that it can be decomposed into irreducible representations, correct?
Yes.
So that irreducible representations will be SU2, isn't it, sir?
No, no, no. See, irreducible representations are all of dimension 2L plus 1. And if you want to
Because
ask what are the symmetry adapted basis functions, and they will become your spherical harmonics for SO3.
why? Because there happens to be a connection between SO3 and SU2 in
Yeah,
theory,
yeah,
I
but that
guess.
is not like this. SO2 and SU3 has got some homomorphism.
Yeah, yeah, exactly, sir.
Yeah,
Yeah.
yeah, yeah.
So I thought that here we have to make this SO3 into irreps of SU. Right, what I thought.
No, 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 it's not like that. Okay, so let me just give you that. See, by doing some kind of a dimensional analysis, you can show that if you have a if you have V of R is equal to some V naught into R to the power some K, let's say some kind of a power K, then you can show that I'm not going to show now. By just dimensional analysis, you can show that this energy will scale like n to the power 2k divided by k plus 2. So this is basically a relation between energy and the quantum number n. This you can do either by pure dimensional analysis, or you can go to Bohr quantum theory, Bohr-Sommerfeld quantum theory, and from there also you can get this result. So now the question that I asked is that you have minus k divided by r power b. Okay, that is the potential you are going to think. Okay, this k and this k are not same, so let's call v naught divided by r power b. So now I said E is going like 1 over n. Okay, E is going like 1 over n. So what is this b? That is the question that I asked. Okay, so in this case k is equal to minus b. So it is minus 2b divided by minus b plus 2. That is equal to minus, sorry, what am I writing? So let us say 2k divided by k plus 2 is equal to minus 1. So 2k is equal to minus k minus 2, correct? So 3k is equal to minus 2, or k is equal to minus 2 by 3. So k is equal to minus 2 by 3 means you have to put the value v naught into r to the power minus 2 by 3. That is equal to v naught divided by r to the power 2 by 3. So the value is r to the power 2 by 3. Of course, you will, if you, it's very simple to derive this. In fact, you can
So,
just do dimensional analysis.
sir, I derived this using WKB approximation.
Yeah. So you can do in many ways. Okay, even just by using Bohr Sommerfeld thing, you can do that. Okay, so that is
I think it's a general expression for any power law potential that energy dependence to n. That is what it is derived in prefix, where they are told that relation between E and n has been derived for a general power law potential.
yes, yes. So this is the one, and the other problem I will check. I don't remember. But,
Sir, I think you made a mistake, sir, then. For sure, sir, because I checked it twice, thrice, 4 times. So happens that it happens to be two. It's not.
so I don't know. So I was so did I give a result like this of 3 2
1 by root 2, 3, 2 plus
1
plus 1 by 2. Oh, no, not 1, sir, just 3, 2.
3
Okay, 1 by 2,
uh,
3,
2 2, sir. 2
2,
2, and then plus
2, 2, and
plus
plus
half
1
of
by
2 0.
2, 0.
okay.
And you told that first you made LZ measurement and you get 2. And you
2
just
x cut.
Square root 2 3 2 plus 1 by 2
3, 2.
2 2.
This is what you get after the first measurement. And so that you have to renormalize it. In this case, renormalization happens to be 2 square root of 4 by 3. Square root of 4 by 3. And it is, sir, it is square root of 4 by 3.
Square root of 4 by 3. Okay, so that will be this state will go to root 2 by 3 3 2 plus root 1 by 3 2 2. And then what is the thing if L square is measured after that?
Yes, the probability of measurement of x
L square is equal to L is
getting
equal to
3.
3.
L equal to 3.
So that should be 2 by 3.
Yes.
So that 2 by 3 is not there. That's what you are saying.
Yes.
Okay. So maybe what I thought, what I did was I initially wrote it like this. When I wrote the state, I think when I was trying to find the answers, I thought I have this as 1 by root 3. Okay, so if this is 1 by root 3, then it will become 4 by 7. Correct?
Which one 1/3, sir?
No, what I'm saying is that I wrote this as 1 by root 2 when I wrote the state, but when I was working out answers,
Oh,
I
you
found
wrote as 1 by.
1 by root
Okay.
3. So that is why I think I wrote it as 4 by 7.
This is the answer.
Okay, okay, fine. I think since 2 by 3 is not there, I think many of you have written wrong answer as correct answer. Okay, so don't worry, nobody will be penalized for that question. Okay, so we can start.
Thank you, sir.